Yeah, so I'm going to talk about when your big data seems too small, and I'll talk about a few kind of very basic settings where perhaps surprisingly you actually can squeeze your data a little more than you think you can and get a little more information out. So the kind of question that underlies a lot of my work is the following. So say you're given data that's drawn from a very complex distribution. So what do we mean by complex? So maybe it's very high dimensional data. Maybe the data is drawn from a large discrete domain or a large alphabet. If you think about kind of genetic mutations, there are lots of different places that can be mutated. This is distribution over a very large alphabet. Or maybe the data is drawn from a complex distribution where maybe the alphabet isn't that big, it's not that high dimensional, but they're very complex dependencies. So like natural language, right? We don't use that many words. We have lots of data, but all the complexity is encoded in the dependencies. So given data drawn from such a complex distribution, even if you have a lot of data, the empirical distribution of the data is often misleading. Okay, so the underlying distribution is very complex, and you don't have that much data in comparison to the complexity. The empirical distribution is often misleading. And the question is kind of in this undersampled regime, how can you actually recover accurate information about the underlying distribution? So we're basically asking, we don't want to understand the structure of the data. We want to understand the structure underlying the data, okay, the structure of the phenomena underlying the data. So I won't belabor the motivations. One thing I wanted to draw your attention to, though, is this kind of apparent paradox. So as data sets have grown, we're actually increasingly faced with this problem of being in the undersampled regime. I guess just maybe one parallel is to think about where computing was back in the 70s. Computers were getting faster and faster and faster, and lots of people said, why do we need efficient algorithms? Computers are getting so much faster. And the faster your computers are, the more important it is to have fast algorithms, because the bigger the discrepancy between what you can actually do if you have fast algorithms versus slow algorithms. And I think that's being realized in the kind of big data domain. The bigger your data set, the bigger the discrepancy between if you actually use your data kind of to its fullest extent. And the second point is, we've heard a lot about kind of all the successes of machine learning, but there's still a lot left. So most of the very successful machine learning systems, they don't use their data all that efficiently. They have lots and lots of data, but they're not extracting all that much information from each data point. And this is no offense to Percy and other NLP people. So humans kind of learn to speak after hearing maybe 50 million words. Okay, this isn't 50 million unique words, right? This is 50 million utterances. Most of them are, potato, potato, potato. Yeah, anyway. And computer systems, we pump in the Wikipedia corpus over and over, and still kind of we're thrilled if they grasp kind of basic grammar and semantics. Okay, so we're not using the amount of information in our data sets to its fullest extent. So I was going to talk a little bit about a couple of extremely basic settings for which you can actually get a little more information out of your data than you think maybe would be possible. Okay, so we're going to think about the most simple setting. We give an independent draws from some distribution, and it's a distribution over some discrete support. So think of this as a distribution over species of fish in some lake. Okay, so we've gotten 6 independent draws. We've seen 3 different species. What can we say about about the underlying distribution of fish in the lake? Okay, so the empirical distribution of the sample. This is a maximum likelihood distribution. Maximizes the likelihood of having seen exactly this sample, but maybe it's not a good estimate of the underlying distribution. Okay? So there are lots of relatively naive-sounding questions that we can ask. So one question is, to what extent can we denoise the empirical distribution without making any assumptions on the true distribution? So given some samples, is it possible just to look at the samples and to say, actually, I know how this empirical distribution is wrong and fix it without knowing any domain knowledge? Is this possible? Other sorts of questions are, well, say we just want to accurately estimate some property of the underlying distribution. Maybe returning the property value of the empirical distribution is not what we want to do. Okay? So how can we get better estimates of underlying properties? Okay, so we'll start to kind of think about what we might be able to say with these two questions kind of in the back of our mind. Okay, so this is just a thought experiment, and it's meant to convince you that maybe there's more things that one can do than might be apparent. So suppose we take 100 million samples, 100 million independent draws from some distribution, and we see about 1 million domain elements. And suppose we see, this means that most of the domain elements maybe we see 100 times. And I'll plot the histogram of the frequencies with which we see these million domain elements. Okay, and this is an actual data set. I drew this from MATLAB. I picked some distribution. I drew 100 million samples from it. And this is a histogram of the frequencies with which we see the different domain elements. What does this mean? So this is 100 here. Most domain elements we've seen 100 times. Some domain elements we've seen 120, 130 times. Some domain elements we've only seen 90 times or 80 times. And now the question is, I'll ask you, looking at this data, what distribution do you think I drew these samples from? So does anyone want to scream something out? Sorry, what was? Okay, so people are saying things like normal distribution. That doesn't even actually parse. So this is a plot of the histogram of the frequencies with which I see the elements. So the distribution itself is a distribution over, species of fish. We've seen roughly 1 million species of fish, and this is saying that there are lots of species we've seen 100 times. Some species we've seen more, some species we've seen less. Yeah, okay, great. So, phrased differently, suppose someone says, look, there's some species that I've seen 120 times. What do you think its true probability is? And the question is, well, are you going to say, well, I think it's 120 divided by the number of samples, divided by 100 million, or are you going to say something different? And the suggestion was that actually, maybe these samples were drawn from a uniform distribution over 1 million domain elements. And why does that make sense? Well, suppose the samples had been drawn from a uniform distribution over these 1 million elements, so all the true probabilities are identical. What would we expect this plot to look like? And the answer is we'd expect it to look exactly like this. Most things we'd see roughly 100 times. Some things we would see more, and some things we'd see less. But you'd expect you'd expect this plot to look roughly like this, roughly like a Poisson distribution of expectation 100. Okay? And this implies that, this guy that you saw 120 times, it's probably no more likely than the guy you've seen only 80 times. Both of these things probably occur with almost the same probability. Phrased differently, suppose the true distribution had a significant variation between the probabilities. Suppose there actually were a decent number of species that had a slightly higher probability and a lot of species that had a slightly lower probability. When you take into account the sampling effect, you would expect to see something that's even wider than this. So if there was a 10% variation between the true probabilities, after you take into account the kind of sampling noise, you would see something even wider. So I claim you can very robustly, if you ever see this, you can very robustly conclude that, the true distribution from which this was drawn is very close to uniform over 1 million domain elements. And in fact, these guys that appeared 120, 130 times, most of them are no more likely than the guys that only appeared 80 times and 90 times. Okay, so what does this actually mean? I mean, the empirical distribution, the probabilities are off by kind of, plus or minus 10% for a lot of these elements. And I'm claiming you can actually denoise this to get, extremely accurate estimates of underlying probabilities. Are people on board with this? It seems a little magical, but we're not using any assumptions about the underlying distribution. All we're using is the assumption that our data was drawn independently from some distribution. We're saying the only distribution we could have drawn things from that would have given a picture like this is a distribution extremely close to uniform distribution over a million elements. Okay? Are people on board with this? Okay, so this is a little magical, right? We've taken our samples, we've thought about what our samples look like, and we've said, look, I understand the process of random sampling, and hence I can remove some of the noise from the sampling process. I can correct the empirical distribution of the samples. So I guess the obvious question is, how general is this? Like, if you just give me some data, how much should you expect me to be able to actually correct things? So we have a few results that kind of characterize this. And I'll state a few results, and you can think of these as different rephrasings of this. So one way of phrasing this is, if for sufficiently large sample sizes, if you give me n samples from some unknown distribution, I can recover an approximation of this distribution, which is almost as accurate in total variation distance, as if you knew a priori the unlabeled vector probabilities of the distribution. So, okay, so maybe I'll say this differently. So, suppose someone told you there is a distribution of species of fish. There's some species that occurs with probability 0.5, some species that occurs with probability 0.1, some species that occurs with probability 0.05, but they don't tell you which species have these probabilities. They just give you this unlabeled vector of probabilities. And then you take your sample, and your job is just to assign the labels to these probabilities. And the claim is that for sufficiently large n, we can learn the distribution as well as if we already had this unlabeled vector of probabilities given to us, and our only job was to label things. Okay. So, right, so maybe I'll give a very silly example. Okay, so why is this a little surprising? So it's not really true for small sample sizes, and I'll illustrate that now. So suppose I tell you I have a distribution of coins in my pocket, and your job is to learn it. So I'll spoil it. So actually, I just have a distribution over 2 coins in my pocket. One of them is a dime. One of them is a nickel. And if I were to draw independent samples, and you were trying to learn this distribution of coins in my pocket, in general, you need to estimate what fraction of the coins is a quarter and what fractions is a nickel. If you want to estimate this to error epsilon, you would need 1 over epsilon squared samples. If, however, I told you the unlabeled vector of probabilities, I said, look, there are 2 domain elements. One has probability 0.5, the other is probability 0.5, and your only job is to assign the labels. In general, you'd expect that after 2 samples or 4 samples, you'd have a very high probability of having seen a quarter and a nickel, and you would just know the distribution. Once you see 2 different domain elements, you know the distribution. But it turns out that this phenomena, this difference between how well you can learn if you have this unlabeled vector of probabilities, sort of disappears for large n. Okay, so if you didn't really, if you weren't on board for this, that's okay. A different way of stating this result, or a different sort of interpretation of what's going on under the hood here, is if you're given n independent draws from some unknown distribution, you can recover the frequency spectrum, so you can recover the unlabeled vector of probabilities as accurately as the empirical vector probabilities would have been if instead of having n samples, you had n times log n samples. So you might wonder, to what extent can you denoise these distributions? Well, essentially, it's as if you had an extra factor of log n samples. Okay, so this, if you're not on board with this, that's okay. This is the most accessible result. Given n samples from an unknown distribution, say your goal is to estimate the number of new domain elements that would be seen in a larger sample of size up to n times log n. this is what you can do. Okay, so you give me n samples and you ask, how many new things do you think I'll see if I give, if I give you a second sample that's much larger, and you can answer this. Okay, you can answer this very accurately. And this logarithmic factor is tight. Okay, so maybe I'll skip this and just, so there are lots of practical applications of this. And basically what this means is you can answer questions of the following form. You can answer questions of, what's the value of collecting more data? Suppose you take 10 times as much data. How much new stuff will you discover? Or you can start asking questions like, how much data is necessary before we're likely to see, almost all of the mass in the distribution? Okay, so if you think about it, you have, so you have a self-driving car that's recording phenomena, and you want to know how many more miles do we need to drive before we're likely to see, 99.9% of all the phenomena that we're likely to encounter. And this basically says that, you can estimate this very accurately up to windows that are kind of logarithmically sized larger than the amount of data you currently have. So just to give a, there are many possible applications of this. One that we looked at, so this is joint work with James Zhu, who just joined the Biomedical Data Sciences department at Stanford. I think he's in the back somewhere. Was applying this to genomics. So at the Broad Institute, we have 60,000 genomes of healthy individuals, and they're trying to raise money to sequence another 1 million individuals, and they basically want to know, what are we likely to discover if we sequence more people? Okay, so what's the value of sequencing 500,000 more people, 2 million more people, 10 million more people? And phrased a little more specifically, they wanted to know, how many new medically relevant mutations are we likely to see? And I guess the punchline is, you can extrapolate to samples that are larger by a factor of this logarithmic effective sample size. And in this genomic setting, the effective sample size, it's kind of the number of genomes multiplied by the kind of number of mutations you see per genome. So this is actually quite a big number. This is right. So I'll put some plots up. So the following is something that occurs at Stanford Hospital, occurs at some other hospitals. So if you go in and you're very sick, it often happens with little kids. They don't know what's wrong with you. They sequence your genome, and they look for genes that have they look for broken genes. They look for genes that have a loss of function mutation somewhere in them. And what do? Well, most people have at least, most people have maybe 1 or 1.5 genes that have one broken copy somewhere. And they sequence your genome, they find the broken copies, and then they look up and they say, how serious is it that this copy of this gene is broken? So they have the data set of 60,000 healthy people, and they say, how many of these healthy people also have the same broken gene as you do? And if the answer is, lots of people have it, they say, this is probably not your problem. If you're the only one, or there are very few healthy people with this broken gene, they say, this might be causing your sickness, and then they look into that. And we have 20,000 genes. We only have 60,000 genomes sequenced. The question is, how many more genomes might we need to sequence before we kind of get complete coverage of the broken genes that are kind of allowable without making you sick? And we can use our techniques to do this. So this is a validation of this approach. So we have 60,000 genomes. Suppose we only look at 6,000 of them, and we try to extrapolate how many more genes with loss of function mutations would we find in healthy people if we actually had 60,000 genomes. Okay, so pick a random 10% of the data we have, look at that, and see if we can extrapolate out what we would expect if we actually had all of our genomes. And the blue line is the truth. The red line is the average of our estimator over different cohorts of size 6,000, and the blue and the red lines are basically on top of each other. So this is just an illustration. Okay, so maybe I'll end here. And I guess if I can leave you with one punchline, it's that many of these extremely basic questions, can you denoise empirical distributions? What can you say given more samples? These extremely fundamental kind of mathematical questions, which are very practically important, are still largely open.
Please join me in thanking Greg.